Okay, George Kaye will be presenting a fully compositional theory of results.
Hey, thank you very much. Hello. So I finally lucked out with my conference talk slots and got one on Friday, which I was very sad about when I discovered it. But I'll try and make it nice and fun so everyone can not think too hard. But yeah, so what are we going to talk about? I'm going to move a little bit further away so I can see. So yeah, we could talk about digital circuits, right? And what is a digital circuit? You can say I've got this nice stock image of something I found on Google. Doesn't really mean anything. But what I actually mean when I'm talking about digital circuits is I mean sort of these circuits made from wires, these components, these logic gates, you all connect them together. So not things with resistors or transistors and stuff. It's just these nice basic logic gates or nice fun things. So, and what we actually want is, this compositional theory of digital circuits. We're categorists, right? We want things to be composed. So what I take this to mean is that we have, we can have some blocks and we can put them together in all these ways. We don't need to look inside the boxes or anything, just smash them together based on the interfaces and not worry about anything else. And yes, obviously we like using string diagrams because it makes things a lot easier to do. And they look quite nice, and I spend far too much time making these pretty diagrams, coming back to them later, making them look even prettier, and like spending hours on it. It's a hard life. But yeah, so how do we get here? Why am I speaking to you here today about circuits? So back in 2003, so what over 20 years ago now, so Yves Lafont did this work on the algebraic theory of Boolean circuits, which already sounds, I think, a bit like digital circuits. We have these logic gates which operate on Boolean values, and we compute sort of functions with them. So it's already quite nice. But there's a problem with these things. These Boolean circuits they are just functions. They're functions. They always act the same way. There's no memory or state or anything. And to make exciting circuits, we want state, right? We want to be able to hold things in our memory and come back to them later. So fast forward a little bit, 2016, a little bit closer, and then Dan Ghica, my supervisor, and Akim Young and Aliam Lopez, they worked on this categorical theory for digital circuits, for digital sequential circuits, they're called. They have stuff happening over time, feedback and delay and things. And this was a nice piece of work. Like it's probably the paper I've read the most in my life because I keep having to go back to it. But although it was very nice, very good foundational, it wasn't massively formal. It was like a lot of things that seemed right, but it wasn't done quite rigorously enough. And I can say that because Dan says it as well. So I'm not actually being that brutal. So we fast forward a little bit more, 2019, and oh, I came along, hooray. So I meet with Dan, started my PhD, and he's like, oh, do you know category theory? And I say, no, I have no idea what this is. But he's like, okay, that's fine. But do you want to do stuff with circuits? I'm like, yes, this sounds much better. Okay, I'll do that. And then also along came David Sprungler, Dan's postdoc, who said, oh, I'll help too, because David Sprungler is a very clever man and has helped a lot with this project. So if you've been to HT before, you might be thinking, like, hold on a second, like, you've done this before, right? I was here in 2022. I gave this talk already. I know everything. But no, it's different. I've improved it. It's become better. I just keep getting all the feedback from all my paper rejections and making it slightly better each time. And I hope that this is finally the stuff that's properly good because I'm submitting the thesis next week. So if it's not good, well, I tried, I guess. But yeah, so strap yourself in because we're going again. We're going on for the final time. We're going to talk about circuits. So what do we need to do when we talk about circuits? We want to first define the syntax, right? What do we use to build up our circuits? So first of all, we have these combinational bits. So these are the Boolean functions, the ones that Lafont was doing back in 2003. And these compute functions, there's no memory or anything. So we have these sort of logic gates, is classic and or a not gate. And then all the other classic categorical structure we're used to. We have these comonoid and monoid, and we have a density and symmetry. And yeah, as we all know, you can put all these things together. You can freely generate yourself a symmetric nodal category of combinational circuits, these nice light blue ones. And then, yeah, these circuits are easy. These are nice to deal with because it's just functions. That's all. A little remark is that we do actually do it a little bit more generally than this. We parameterize it over some signature, But because I don't want to do everything that generally, we'll just deal with this one for now, this nice, sort of well-known one. I do all my examples in this anyway. So yeah, so these are the combinational components, these nice blue components, the easy ones. But unfortunately, we can't just do all the easy work. We have to do some actually interesting stuff. So we need to add something sequential, the state to make our circuits do good things. So we're first going to add some values. So first of all, we have our standard false and true things, but also because of things which I'll mention later, we're also going to have another value, which is this sort of top value, this short circuit. And the way you can think about this is that our values form a lattice. So we have at the bottom, we have this is a bottom element. This is the disconnected wire from the sort of the blue section, which means no information. In the middle, we have our classic true and our false. This is exactly one piece of information. We know what to do with this. We know how it works. But at the top, we have the top element, and this is the short circuit. We've tried to cram both a true and a false into a wire at the same time, and we sort of an overabundance of information. There's too much. And so we need this to deal with the join that we saw in the previous slide, because if you ever join things together, things could go wrong. And then on the other side of things, as well as our values, we're going to need to have a notion of delay. So we have this one little generator. You can think of it as like a register or something, like something goes in, waits a little bit, comes out next time step. And we also have this feedback, this trace operator that we can connect an output all the way around to the input and make a feedback loop. Sure, yeah. No, this is why we don't do the delay trace. We want to have this potentially sort of non-delay guarded trace as well. But yes, very good. And yeah, I think it mentions later. So yeah, this is so good question. Non-delay guarded feedback. This might be. The delay is a distinct thing. Yes, these dark green circuits are the interesting sequential circuits. Yeah, so circuits then, as we said, we can bash these all together to make circuits as morphisms of some symmetric trace for nodal category. And yeah, using our favorite operations of composition, tensor, and trace. So a lot of the questions I get from people is that why are we doing it with the trace? Why don't do some funky Frobenius compact close thing? You make it out of this fork and join and whatnot. But the problem is that, yeah, we want to have copying. We want to have things copying through circuits. So which means that we have this sort of well-known naturality equation, and then subsequently we would be able to sort of push over the disconnected bit over the fork, and then you rip apart your trace. So we don't want that, because this means that you have this feedback loop and suddenly it's gone. You don't have a feedback loop anymore. And this is sort of a result of circuits being, or digital circuits maybe being very causal in nature. It's all very, things come in and propagate round, whereas other things are more relational in nature, but we're not relational, we're just functional. Yeah, so we do actually want trace to be one big operation stored in one go. So yeah, where were we? So this was me in 2022. It was the day after the hottest ever day in the UK. I was not in a good state. So I was quite hungover because we sat in Glasgow Green drinking a lot. But I did my talk anyway, and I think it was fine. I had an okay time. But what did I talk about then? So what I sort of talked a lot about was what are the denotational semantics of digital circuits? Like what's the mathematical meaning? And I think this is hopefully fairly intuitive that this is going to be functions on streams, right? I think we've seen streams earlier in the week. Yeah, things are happening over time. We have a stream of inputs coming in, they get translated into a stream of outputs. So yeah, a bit like I think Eleanor did to talk of this Mealy machines, right? Circuits are like Mealy machines, they take in streams of inputs. And so when we have this notion of denotational equivalence, that when two circuits have the same semantic stream functions, then we can draw this little funky wiggly equals. But I'm not going to talk much about that because last time I took too long and didn't finish the talk. But there's some stream functions in the background. And the other sort of fun thing I talked about last time is that because, as I mentioned, we have this idea of this trace, this non-delay guarded trace. And normally people in circuits are really scared of this because when you have a non-delay guided trace, it makes weird undefined behavior happen. Now, which we don't like the undefined behavior, but we do still want to have it because we want to do things with all circuits. We don't want to have the sort of delay trace kind of categories because we like having yanking around. We want to be able to pull out wires. So we want to keep in the non-delay guided trace, but it gets in the way. So we want to get rid of it somehow. And by following some sort of cleanly fixed point argument, because we have functions and our functions are monotone and we have a finite lattice of values, we can just say that, oh, anything with a non-delay guided trace can actually be just copied like this. You start off with a disconnected thing, you iterate it a few times, and you reach a fixed point because you're in this finite lattice. And just do this. We have the same thing, same string function, but no non-delay guided trace anymore. So hooray, it's a lot easier to deal with. Yeah, so that's that bit. So those are the two main bits I think I talked about last time. I also did some sort of hacky equational theory thing because I was still trying to work out what was going on. And so it was a little bit confusing because some of the equations seemed kind of pointless. There was one that sort of did everything for you, and it was like, ooh, is it good enough? But this is what I'm back to tell you about today, is that how we sort of did solve this problem. So yeah, denotational equivalence, it hides the structure of terms. Like you have a circuit, and nice, you build it up, your nice building blocks, and then you turn it into a stream function, and oh wow, it's just a stream function. Like it turns inputs into outputs, fine, but why does it do that? And we want to sort of reason more syntactically, like by going, oh, we have these blocks, we're going to go, boop, 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 change them around. And so we have two ways of sort of doing this now. So the first one is operational semantics, which I again sort of mentioned in Glasgow, but then I'm going to tell you more about it. It's changed a little bit, a tiny bit. And then we also have an algebraic semantics, which is pretty much new. There's some bits I think which were poached from the operational semantics and moved across, but the algebraic stuff is pretty much new, I think. Ding dong. Okay, so suppose we have two circuits with the same denotation, right? So they have the same behavior, they do all the same things. What's to say about the structure? This is just what the last slide said, right? But we want to find a set of reductions that we can say why are these circuits behaving the way they are? Why does this inputs sort of go through the circuit, propagates through? What are the transformations happening that make this happen? So yeah, we want to do a series of step-by-step reductions to find out what a circuit does. So yeah, well, first of all, we have a circuit. Let's put it into a nicer form, right? Let's make it a little bit less confusing because there could be anything in this block, right? So what we're going to do is we're going to drag out sort of all the delays, all the values and things. So we have this nice combinational bit in the middle. This is just a function. And we have the delay in the values, the sequential components, all on the outside. And this is another reason why we want to have this yanking axiom around, because it means we can just make these loops. We can sort of put a loop in, drag everything out. So it keeps things nice and separated. Yeah, and that's entirely just by axioms of trace categories, right? We haven't done anything clever, we've just dragged things out. And let's make it even more simpler. Let's introduce a little bit of notation. So you can imagine this sort of idea. It's like a delay register, but it's got some initial value, which is how you might think of a register really. Like it's going to be initialized or something, right? And we can just rewrite the two delays and the values. We're going to view these both as type of registers. Like a delay is one where it starts off with bottom and then things are filled into it later. And a value is a register which has this initial value v, and then sort of, but whatever fills in next is a bottom. Right? There's nothing interesting afterwards. Okay, this is like an initial state, and then this is a state that gets filled later. So this just means that rather than having to deal with the value and the delay separately, we can just reason about it just in terms of this like one syntactic construct. And yes, this means that any circuit, any green circuit F, any circuit which might have sequential stuff in it, we can sort of transform it into this bit here, where we have this blue bit, and we have registers, some green registers that all go around. And this is very nearly like a Mealy machine, right? You have sort of a function that transforms a state into an output and the next state. It just goes around and updates the state. But I said this angry, non-delay guided feedback is still in the way. But fortunately, as I told you a few slides ago, we actually have a way of getting rid of this. We can just sort of copy this circuit out, and we can transform this circuit into this circuit, where this is like, that's F hat, that's F tilde, so a little bit different. Yeah, but any green circuit means we can get from, so whatever's in there, we can find some sort of combinational bit in the middle and give it a state on the outside, which has a loop around it and updates over time. So that's nice. So we have sort of a nicer form for circuits. Like we can divide between the sequential and the combinational stuff. Okay, hope everyone's still following. So what do we actually want to do with an operational semantics? Like what are we going to do? So what we want to say is, if we have some green circuit, some circuit F, and we give it some input register here, so this is like maybe like the first element of your stream. We want to say, what happens to the circuit? What's the output of the circuit? What does it sort of pipe out? And again, how does the circuit change? Well, how does the internal state of this circuit change? And yeah, how does it process the value? And to do this, we'll need a few more reductions. So then these ones, I think, are fairly self-explanatory, how values interact with the other components. You can know that the gate will process its input, the fork will copy things, so that is where our copying comes in. If you have the join, this is where we use this join in the lattice. So true join true is true, but true join false is going to be this undefined, well, overdefined top element. And if we have this sort of stub at the end, it just vanishes, goes away. And these little reductions here, this means that any of these blue circuits, again, these are all the combinational components, we can always reduce one of these blue circuits with an input to some output values. So that's already helpful when you're dealing with the blue circuits. But we're not just dealing with blue circuits, are we? We're dealing with the green circuits. So how do we use this to also deal with the sequential stuff? So what about delays? Yeah. So first of all, again, we'll think about the combinational case. We have some sort of value applied to some sort of circuit. How do we deal with this? Well, if you remember that this register notation, it's just a join of some value and then some delays. So what you might think is, oh, perhaps we could push this F across the join. Maybe it's like the copy. Maybe it's natural. But it's not quite natural. Like the join isn't always natural. But because we're operating in this sort of special case, so we have the value will do things in the first instance, like they're the initial state, and in the future, everything else comes this way. We can actually push it across the join here. So that's good. We can copy this blue circuit and say, we have a bit for what happens now, and we have a bit for what happens later. And if you remember, oh, now we have a value and a blue circuit. So yeah, we'll be able to propagate this value across and find some more values. Yeah, this is cool. It's called the streaming. I think it's like a legacy name from 2016, but that's just the name it's stuck with now. So yeah, so that's actually all the pieces we need to do some sort of operational semantics across the green circuit. So how do we do it? I'll just sort of blast through the sort of reduction strategy. First of all, we put a circuit into this special form. We get this core and state. This V is our input that's about to be propagated through. And then what happens? Well, we have a blue circuit with some green inputs. So we can do this copying thing. We can stream the inputs over the circuit. And then because if we have green things applied to a blue circuit, we can reduce them through. We can propagate it across using these rules. And we get some more stuff. And then we reapply this register notation. It's a join with a delay. So we have a next state and an output. And then just to make things look nicer, we'll swoosh around the T. And we're back to basically what we had at the start, right? But now we have a different state in our circuit, and we've pushed through the input to be an output. So we've got exactly what we wanted. We found out what's happened to the circuit and what the output is. And yeah, and if you want, you can sort of compress this back into a nice green circuit if you don't really care what's happened. Yeah, then obviously when you're talking about operational semantics, you're then always thinking about, well, when are these things now observationally equivalent? Like when this is our notion of equivalence of operational semantics. And so we're dealing with circuits which have, a finite number of states, which means that there's only a finite number of sort of words they can fit in these states, right? Because again, we're working this finite lattice. So there's a maximum number of internal states these circuits can sort of assume. So all we need to do is check, perform the procedure from the last slide for this number of steps, and we're guaranteed to have some sort of reoccurrence of an internal state. And then we're done, and we can say, oh, well, now I've seen all the possible behaviors these circuits might have. So then we'll know, oh, are they the same? Because they'll have the same behaviors. I think that's just what the next slide says. Yes, we just need to check for all this number of input lengths, see, can we find a recurring internal state? And then, yeah, do these two circuits do the same thing? And yeah, and that's operational semantics. And we have that if we have two circuits which are denotationally equivalent, if they have the same stream function, then doing this thing with doing these reductions across the circuit, this is the same. They can only do one if you can do the other one as well. So that's obviously very useful to have, very nice. And yeah, we have this nice little isomorphism. And one little remark, so I get this occasionally as well, is that other people do operational semantics a bit differently. Like they have this sort of idea, you have maybe some time and stuff, and then you push a K in, and it puts K in, K out, and some time changes. But this looks a bit different to ours, right? We did stuff, we actually sort of propagated stuff across. We changed the structure of the circuit. And this is because we actually, for our sort of interests, we actually want to say, can we transform the circuit? We want to maybe do some partial evaluation of stuff. Can we propagate some stuff across and see what that does to the circuit and how it changes it? So they're both sort of ways of doing it. We've chosen this one rather than that one. Yeah, so this is nice. You can do this automatic procedure and everything, but it is super exponential, right? If you have a load of inputs, you have to check a lot of stuff before you can check if things are equal. So can we do better? And well, yeah, we can. We could do stuff with equations. I'm realizing I am running quite out of time now, but we'll see how far we can get with this. I think it's a shorter bit than operational, but fingers crossed. Yeah, so first of all, we'll have equations just to get back to this nice form we had before, because that's a nice way of doing things with circuits. We'll do it a little bit differently before. We'll have these sort of smaller equations, but this is the same thing. We can use equations to transform any circuit into something that looks like that. And yeah, so what do you do when trying to make an algebraic semantic to something? How do you get the right equations? Well, you want to try and sort of normalize it, right? You want to get some sort of normal form, right? That's the general way of doing things. So yeah, why don't we try doing that? So say we have some sort of procedure that we can get any circuit in this, any sort of blue circuit into a nice normal form for some sort of function. Now, for this example, it looks a bit like this. It's a bit funky. Effectively, it's because we have 4 values. It's just a sort of booleans times by booleans. So we have sort of a circuit that deals with the sort of negativeness of a value, and a circuit that deals with the positiveness of a value. And we would like some equations that get any sort of blue circuit into something that looks like a bit like this, a normalized circuit. And I'm going to sort of blast some equations in your face. They're fairly standard stuff. Like we have push things across. You've got associativity and distributivity and stuff. And I'll surprise there's more as well. There's another load of circuits, but these ones are again very standard stuff. And okay, so these sort of things mean that we can translate any blue circuit into one that looks like this. We can find like a normal form for our combinational circuits, which is a good start. David's standing up. So we have these circuits, these equations, and then, okay, cool, that's fine. That's the blue circuits. But again, we're not dealing with blue circuits, are we? We're dealing with green circuits. So how do we get from here to here? Well, we want to be able to encode the states. We want to be able to basically, if we can think of the Mealy machine perspective, we want to have some sort of homomorphism between them. And we do this by saying, oh, we have some encoders, and these work in the way we might expect. And then we have some more equations. Again, these ones fairly standard. And we just have this sort of special one to say, when we're in the right context, we can sort of paste in this encoder decoder pair so we can translate from one to the other. And then, so we can do encoding. And then, is that enough? We're nearly there, we're nearly done. But it's not actually enough, because even if you'd have two things that had the same states, they might not actually have the same behavior in their, sort of their blue bits. Like here, these are different, but they work because they only have, you know, the right sort of states happen. They don't have anything that will make weird stuff happen. So we do need one sort of final thing, or sort of family of equations. It's just saying that we say to map through things, if sort of the cores agree on the states that matter, like the ones that are actually going to happen, then yeah, we'll be able to translate between them. So this isn't maybe an equation per se, but it's like a family of equations. You have to find out which ones are okay in this context. And yeah, and that is enough. That's all we need. We can say, if things are denotation equivalent, then we can make them equal in the equational theory. And we have this nice map between denotational and algebraic semantics. And yeah, there we have it. So we just defined these three different semantic digital circuits. Well, one of them I sort of said was there and then didn't do anything with. We have denotational with stream functions, operational with reductions, and algebraic with these equations. And obviously, as you'd expect, we have this nice triangle between them. Everything's isomorphic, so you can do things in whichever way you want, whichever way is the nicest at that possible time. And yeah, this gets us this fully compositional theory of digital circuits that I've been doing for, what, 4 years now. So we did it. Thank you very much.
Clarification question. So you said your base category is a trace category. So I understand why you didn't want convenient structure, but is there anything stopping me from still having compact flows? Compact flows without
I think it's because we get some products happening. I think there's some badness when you try and mix the compact flow stuff with the products. I think things, yeah.
Okay, so because it's the product. Okay. My second question: could you go back to slide where you had like 3F?
That one, well, a few slides, that was a long time ago, I think. Oh, there you go.
Could you just explain that quality real quick? Because that's kind of shocking to me.
So think this thing F, this is a function, and it's a monotone function, which I may have not made very clear, but these are all monotone functions. So, and then because we're working in a finite lattice, what we do, we say, what is a function F, of the fixed point of the function F? We start with F applied to bottom, we iterate it, we keep saying F of F of F, blah, 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 and then we're gonna, because we're in a finite lattice, so we start F bottom, we might go F true or F top, but eventually it will stop somewhere. So in this case, this is hiding a little bit here, this is for one wire. It's 3 because we start at the bottom, go up to the true and false layer, up to the top layer, and then we're guaranteed to have found a fixed point.
So that your
well, we like having, because when people design circuits, they do design circuits with feedback, right? So we want to have them around for people to make these circuits, and we want to say that people can design circuits with trace because the trace is helpful for not, because this is a much bigger circuit, right? It's more space efficient to do it with the small one. But when we're just reasoning with it, we will have to sort of unfold it. So it's like, this is nice to have as a design. To reason with it, we can then unfold it. And then later you might go back to have it more compact.
I think one more question.
transformation step 2. They look at relationships and I think that all belongs to semantic. You have a full transformation, instantaneous feedback,
bands.
Mm.
Sets, some semantic structures, this is more concrete.
Well, I'm not very well versed in that sort of stuff. Maybe that's my answer.
Let's see.
Yeah, yeah, yeah.
Let's take a- and we'll take other questions.